Yeah, our third speaker today is Łukasz Mas from Polish Academy of Sciences. And he'll be talking about limit shapes of taquin path and evacuation path in random scale tableau.
Oh, okay. So thank you very much for the introduction. I would like to thank you for the opportunity to present the results. And the results I'm going to present are joint results with Piotr Śniadek, who is my supervisor, in fact. Okay, so I'm starting with introducing some notations. So we are going to draw diagrams on the Cartesian plane. Each boards of the diagram and tableau will be a square of size 1 by 1. And we will draw them in French convention. That is, the entries are increasing from left to right and from bottom to top. For our purposes, it will be also helpful to consider U coordinates of the boxes, which is the difference between its x and y coordinates. We are going to use two operations. In fact, first one is the classic taquin operation, which is defined in the following way, where we create a hole in the left bottom corner of the tableau, and then slide the box to the right or above the hole towards the hole, which has the smaller entry. And we proceed in this way until there is no more box to the right or above to slide. And when we finish the sliding, we remove the box with the hole. The path colored in red is called taquin path, and it will be very important object in this talk. We also consider the modified version of taquin, which applies only to standard Young tableau, and it is defined in the way that we do not remove the box with the hole, but we put the entry, which is the number of the boxes in the initial tableau +1, and then we decrease all entries by 1. In this way, we have a bijection between the standard Young tableau of some given shape, of some fixed shape. Okay, the two problems which we are going to consider is first the typical shapes of the taquin path. So we are sampling a random tableau with respect to the uniform measure over all standard Young tableau of square shape. And we are looking for the taquin paths, which in fact we scale by the square root of the size of the diagram, so that this taquin path fits in a square 1 by 1 with all the Young tableau, and it is the zigzag line. So we are looking for the typical shapes of zigzag lines. The second problem is the problem of the evacuation path, which we defined in the following way. It is the sequence of positions of the biggest box. So here the box with number 100, which is marked in red. When we apply taquin until there is no box to remove. And in this way, we get the evacuation path. So it is the process of observing the position of the biggest box, and we are also scaling the evacuation path, so it fits in the square 1 by 1 on the Cartesian plane, and look for the typical shape of it. In fact, these two problems are equivalent in the sense that the probability distributions of the taquin path and the evacuation path are the same. And it is a general fact which holds for any random standard Young tableau of some fixed shape. until we are sampling with the uniform distribution. And the proof of this uses two facts. First is the symmetries of Robinson-Chest and Knuth algorithm. And the second, well, it is a notion of lazy Jodot-Takao path. The lazy Jodot-Takao path is some sequence of boxes which arises during application of Jodot-Takao. Like only one single application, and you have some sequence of boxes, and well, this would be a lazy Jodot-Takao path. So since these two problems are equivalent, we are going to focus only on the evacuation path problem. The result which will be helpful in our considerations is provided by Pittel and Romik. They found the explicit formulas for the level curves in square-Young tableau. The level curve is a curve which asymptotically, when the size of the diagram is bigger and bigger, separates the boxes with the number with numbers less than alpha and square from the bigger boxes. For example, here in the red solid line, we have a 0.75 level curve. In blue, it's 0.5 level curve, and in green, it's 0.25 level curve. They also found the explicit formula for the limit distribution of the box with number alpha and square on this alpha level curve, or at least in the surrounding, and it's given in terms of the U coordinate of the box. So this result is helpful, since if we are looking for the position of the biggest box in our evacuation path, when we removed 1 minus alpha fraction of boxes, then it's the same as looking for the position of the box with the number alpha and square in a tableau in a tableau arising from applying a modified version of Jodot-Takao to our initial tableau. This means that if we are looking for the position of the biggest box after removing 1 minus alpha fraction of boxes in our initial tableau, then it's the same. Then we know that it lies somewhere near the alpha level curve. Our problem, in fact, is to pinpoint the exact place of this box. And for this, we should introduce some suitable coordinate system, which we call geographic coordinate system on the square. The first coordinate of a point in square will be a latitude, and it is the unique number such that our point lies on the alpha level curve. Okay, the set of points with the same latitude is called circle of latitude, and here on the figure you have some examples of circles of latitudes. The second coordinate, denoted by psi, is coordinate which is calculated as a cumulative distribution function of the limit distribution found by Pittel and Romik in a U coordinate of the point. And we will call the set of points with the same longitude a meridian. And here on the figure, you can see in red the meridian 0.1, in green meridian 0.3, in orange meridian 0.5, in brown meridian 0.7, and in gray 0.9. So here is some system of meridians. If we are looking for some points in a square with some geographic coordinates, we will find the point with the latitude and longitude a half in the square of in the center of our square. And for example, here is a point with latitude 1/4 and longitude 1/10, and symmetric to it about the center of the square is a point with latitude 3/4 and longitude 9/10. So our main results says that the evacuation path converges in distribution to a random meridian. Here on the figure, you have several random geodetical paths and some meridians in solid lines, and these meridians were chosen so that they intersect our geodetical paths but in the anti-diagonal of the square. So the question is, why do we move along the meridians? So for this, we need some suitable parametrizations, which we call the parametrization by time. And in this parametrization, we observe the scaled position of the biggest points in a after removing t fraction boxes from our initial tableau. The proposition below says that if we have two moments of time, two given moments of time, then the longitude of the position of the biggest spots in time in the first moment and in the second shouldn't differ a lot. For example, on the figure you have like the same picture almost like before, and in the colored areas are in a distance 1/20 from the meridians, and as you see, more or less geodetical paths fit in these colored areas. So this proposition should hold. To prove it, we introduce some suitable point of reference, which we call the multi-surface story. In this story, we are observing not a single box, but k boxes with the biggest numbers in tableau, and we assume that they are ordered increasingly from northwest to southeast. And if you apply geodetical to such tableau, then it still has this property that the k biggest boxes are ordered increasingly from northwest to southeast. Okay, such tableau is called Cappieri tableau, and well, we sample them according to the uniform distribution, but only over a Cappieri tableau. We should notice that if k is equal to 1, so we are observing only one biggest box, then we have the same story as before. So we are observing just the box with the biggest number. So from now on, these k biggest boxes will be called multi-surfers, and the boxes below them will be called the water. So the multi-surfers are surfing on the water, and if we have only one box to observe, then we call it the single surfer. Okay, so our aim will be to show that if we remove alpha fraction of water, then the multi-surfers will converge in distribution to the limit distribution found by Pittel and Rock. We will, since this limit distribution is compactly supported, it will be enough to show that the moments of appropriate measure are converging to the proper moments of the limit distribution. Okay, so to the measure. So here we define a measure which gathers as a sum which is a sum of point measures of the u coordinates of the multi-surfers. We can see that, well, if the number of the multi-surfers is bigger and bigger, then these points should gather in some way. And we should also notice that this random measure is a cumulative distribution. The cumulative distribution function of this random measure is the empirical distribution of multi-surfers. So now we are going to calculate the moments of this measure. Then they are also random, but it comes up that if the number of the multi-surfers is bigger and bigger, and also the square of size, the size of square is bigger and bigger, then these random moments converges to the deterministic values, which are exactly the moments, the proper moments of the limit distribution found by Peter and Ron. For this, we show that the expected value of these random moments converges to the proper moments of the limit distribution, and the variation of these random moments converges to 0. So we have a convergence in L2. And to show this, we use a lemma, which is a connection between the representation theory and statistical properties of surfers. If we have a symmetric polynomial and some set of tableaux of a square shape, which has this property that k consecutive boxes, like from boxes with numbers from a to a plus k minus 1, are ordered increasing from northwest to southeast, like in the multi-surfer story, then we can calculate the expected value of this symmetric polynomial calculated at the coordinates of the boxes in terms of character of irreducible representations corresponding to the square shape diagram. So the irreducible representation of Sn square. In terms of the uses Murphy's elements and the projection on the trivial representation. So going to the final proof, so that the longitude in 2 moments of time doesn't change a lot, we should link these stories of the multi-surfers and the single surfer into one. So we construct the common probability space in the following way. First, we sample the water, which will be the same for both stories. For the story of the single surfer and the multi-surfers, for example, with respect to the probability for a single surfer story. Then we sample the position of the single surfer on the water with respect to the conditional probability, and independently we sample the position of the multi-surfers on the water with respect also to the conditional probability, but in the setting for the multi-surfers. And now we first show that we first show the one-side inequality, so that the longitude after time cannot change too much. For this, we first made an observation which says that if we have the multi-surfers southeast, so to the right and below the surfer, they cannot jump to the left and top of the surfer. So the multi-surfers which are southeast to the surfer, after applying jeu de taquin, cannot jump northwest to the single surfer. So their number can only increase. The guys from left can go to right, but well, the guys from right cannot go to left of the single surfer. And then we just compare the empirical distribution of the multi-surfers calculated in moments T1 and T2 with respect to the u-coordinate of the position of the surfer. for the opposite inequality, we can use symmetries of square-Young tableau. But in fact, we can make it in other way. We can consider another story, which is a story of anti-multisurfers, where we consider to observe also cabbage boxes, but here we assume that they are ordered increasingly from ordered decreasingly from northwest to southeast. And for these results, in fact, we used two things. First is formulas for existence of the level curves in square-Young tableau, and the distribution on these alpha level curves with respect to the u-coordinates of the surfers. Bian provides these results for C-balanced Young tableau. These are tableaux which has at most some constant numbers times square root of the size of the diagram, rows and columns. And these results are given in terms of free cumulants of the limit shape. So we can generalize the result I told you about in a minute ago to such big class. As it goes for the applications, with the theory of standard Young tableau, there is also a theory of random sorting networks and a second-class particles which are connected, and these results in particular can be translated into the language of the second-class particles. And we can know that if there is some finish some end setting of the particles, then the second-class particle will behave in some more or less deterministic way, deterministic up to the distribution of its movements. In the very end of this talk, I would like to advertise the summer school on algebraic combinatorics, which will be held next year. It was, well, supposed to held this year, but due to coronavirus, it must have been well cancelled. So it's going to be next year, and it will be, each invited speaker will have 5 hours of lecture and 2 hours of exercises, and there will be Valentin Ferrari, Vic Reiner, and probably Annie Schilling. And also my supervisor is looking for a postdoc, which will live in Krakow probably, so the second capital of Poland, which is a beautiful city. So, well, I encourage you to join the summer school and maybe apply for a postdoc position if you wish. And thank you very much.
Thank you. Yeah, if you stop sharing your screen, you can see the reactions. Yeah. Thank you. So yeah, we have plenty of time for Q&A. So Eric, please go ahead.
Okay, so there was one question from Aditya Khanna, but I'm not sure if I understand the question. So Aditya, maybe could you state your question or explain your question?
So you had these meridians and latitudes, right?
Mm-hmm.
So, and there were these curves on the 1x1 grid, the square grid.
Yes.
So could you transform the square into another surface so that you could see them as straight lines?
Well, more or less, yes. In fact, this result about the second-class particles show that, well, you have some spherical So some articles and some sphere in which these second-class particles should move. It's a direct transformation from one story to the other. So they, well, so yes, there is some transformation.
Okay.
So, and then these meridians are like some ellipses, like half of ellipses, and in this circle area.
Yeah, okay. Thank you.
So we have another question from Dan Patea. What is the definition of second-class particle?
Well, you have particles on the like integers on the real line, and they move, they can jump to the right or to the left. And second, if there is a hole to the on one side of it, let's say, and there can be also a second-class particle, let's say, which is like a second-class passenger, where the real particle can say, "Oh, you should. It's my seat, and you must go from here." Well, it's not a definition, so well, it's not so. It's an easy definition, but maybe I'm not really prepared to answering this question so much.
Okay. Thank you. So I don't think I see any other questions. If there are any other questions, feel free to add them to the chat.
Okay, I guess that's it for Q&A then. And let's thank Łukasz again for his talk.